Hello all, welcome to Osium. It's me Anu. So today we will be discussing about physiology, especially we look into cardiology. So I know you guys have exams coming up. So before that, yeah. So we will have a quick run through in looking into cardiology. So let's start. So the first thing we have something so called electrical activity of the heart. Now coming into it, we have two major concepts. One is automaticity, the other one is rhythmicity. What does this suggest? As the name says, automaticity. It's the capability of something to do something automatically. So, in the heart, we have a bunch of cells which initiate contraction independent of external stimulus, which means a stimuli. So these cells has its own capability to initiate its own action potential. The next one is rhythmicity, which means the ability of the heart to initiate these action potentials in the rhythmic manner. So the regularity of these action potential is called as rhythmicity. I can't speak. I just bit my cheeks today morning. So yeah, talking about the cause. So what is the cause of rhythmicity and automaticity? So we have a thing. We have a group of cells, which I said. These cells are called as the pacemaker cells. So these pacemaker cells has the ability to generate spontaneous and regular action potential. So these action potentials are automatic and regular. So these pacemaker cells, as we all have been like what we have been studying this from I don't know mid school. We have the SA node, we have the AV node, we have a bundle of His Purkinje fibers. So these group of cells are organized into a hierarchy depending on their rate of discharge. So the first one is SA node, which has around 90 to 105 beats, discharges per minute. The next one is the AV node, which is around 60 per minute. And the last one over here is the Purkinje fibers, which has a rate of 20 to 40 per minute. Now, my next question is why is SA node considered as the principal pacemaker or as the main pacemaker? It's because it has the fastest rate of discharge. Okay, so that's why SA node is considered as the major pacemaker cells. Now think, SA node does its work, but after a while, or let's say in an unfortunate event, this guy stops working. So can we allow our heart to like just stop? No, we can't. So what happens? The next guy, the next helper one, which is the AV node, takes the upper hand, takes the role, and starts its discharge at its rate, which is 60 per minute. If both SA and AV node gives up, we have the last one, the Purkinje fibers, at a rate of 20 to 40 per minute. So that's that's what's written over here. It takes over in the failure of AV node. So SA has to give up, then AV has to give up, then what comes? Purkinje fibers come. Now we have a thing called as resting membrane potential of the cardiac myocyte, of the heart cell. We all know, I guess, which is negative 90 millivolts. So what are the factors that helps in maintaining this resting membrane potential? So the first one is efflux of potassium through inward rectifying potassium channel. So I know efflux and inward, it is just the straight opposite. So think efflux occurs when the membrane has a more positive charge, which is in case of depolarization. So after depolarization, when the membrane has a positive charge as compared to its original state, what happens? Efflux of potassium occurs. So that's the first thing. Next thing is influx of sodium and calcium, which has a very tiny role in it. That's why it's written as it contributes a little to this. Then at the end, we have the sodium potassium ATPase. We all know sodium potassium ATPase moves three sodium out of the cell and moves to potassium into the cell. So all these three, efflux of what? Efflux of potassium, influx of sodium and calcium, and the sodium potassium ATPase, which does the opposite work, helps in maintaining the level of -90, which is the resting membrane potential. All right, oh, it hurts. So we have a thing, as I said, we have the pacemaker, and the pacemaker has its own action potential. So now let's discuss about the ionic basis of this. Just give me a minute. So the ionic basis, I'll just turn this on. So the ionic basis of this, so we have three phases: phase 4, phase 0, and phase 3. Now what's phase 4? Let's look into this. This part, the initial part until it reaches the threshold, is called as phase 4. So once it reaches the threshold, it goes to a spike, which is called as the depolarization. That's phase 0. And we have phase 3, which is the repolarization until it hits -60. So what's phase 4? Phase 4 has another name, which is the pre-potential, which means it builds up to the potential. Okay, and this is spontaneous depolarization. So how? So over here we have two major channels which does the work. The first one at -60, which is the RMP, we have a thing called funny channels, sodium funny channels, and sodium calcium exchanger. So these both opens up, leading to a current called as funny current. So that's from -60 to somewhat negative, so it's somewhat -50. Which two channels takes the role? We have the sodium funny channels and the sodium calcium exchanger. These guys work and they initiate their spontaneous depolarization. So once it reaches to a level of -50, another guy opens up, which is the transient type of calcium channel, the T type. So this helps in depolarizing the membrane to a level of -40. So once we reach to -40, I'll repeat this once again after I complete this. From -40 to the peak, we call it as the depolarization, which is the phase 0. So what happens over here? Inactivation of the previous channels, which are sodium funny channels and T-type calcium channels. They both shut off, and another guy opens, which is the L-type, the long-lasting calcium channels. Why? Because it has to stay for a while, and this phase is called as the slow depolarization because it's slow response of the action potential. It's visible over here. I mean, this is short and this takes a while. So once it reaches the peak, what happens? Something that goes up has to come down. So the next phase is phase 3, aka the repolarization, to -60, which is the resting membrane potential. So over here, what happens? The repolarization, as I said, once you move to something, you have to leave behind what you carried for a while. So what did phase 0 carry? It carried the L-type channels. Which channels? Calcium channels. Now they will leave them behind. So L-type will close, and what will open? We have the delayed rectifying potassium channels. So the potassium has to move out of the cell. And what happens? The charge falls to -60. So that's phase 3. So once again, we have the phase 4, phase 0, and phase 3. What happens in phase 4? Phase 4, we have sodium influx. Yeah. So with the help of sodium funny channels and sodium calcium exchanger, what happens over here? It initiates the depolarization to a level of -50 from -60. So this is called as funny current. So once it reaches the level of -50, what happens? a thing called as T-type, transient, short, quick. This guy opens. So what happens? The calcium comes and it depolarizes until the level of negative 40, which is the threshold, the firing level. So once it hits this threshold, what happens? Phase 0 begins, which is the depolarization. So what happens over here? In activation of what? Sodium, funny channels, and T-type calcium channels. These guys shut off. What happens? What opens? L-type, long-lasting, the long one. It opens and it leads to slow depolarization. So after this, it reaches to the peak, the peak of this potential. And over there, what happens? Phase 3 begins, the repolarization. What happens over there? It over there, over there, the L type, the long lasting calcium channels shut off. Why? To fall down. So what happens then? The delayed rectifying potassium channels open, leading to the potassium coming. And what happens? The charge falls back to negative 60 and the cycle continues. So phase 4, phase 0, phase 3, which is the pacemaker potential. It's not the muscle, it's the pacemaker. So I guess it's clear. This is the graph. So we have the phase 4 until negative 40, then we have the phase 0 until it reaches the peak. And what happens over here? We have the downfall with the help of delayed rectifying potassium channels. Am I clear? I guess I'm clear. The next one, we have the ventricular myocyte, which is the cardiac myocyte. So these have a different name, non-pacemaker, because these are not the pacemaker. They can't generate their own action potential. So it needs someone. So this is called as non-pacemaker action potential. So this is divided into phase 4, phase 0. We have phase 1, phase 2, and phase 3. Over there we had phase 4, phase 0, and phase 3. In pacemaker potential. But when it comes to non-pacemaker, we have extra phase 1 and phase 2 over here. We'll discuss. So what's the RMP of a cardiac myocyte? We have a different resting membrane potential for the cardiac myocyte. It's negative 90 millivolts. So what happens over here? The potassium slowly moves out the efflux to maintain the RMP, right? Via the what? The inward rectifying potassium channels. That's phase 4. What happens next? We have the phase 0, the shoot. That's depolarization to the level of positive 20. So what happens over here? The inactivation of inward rectifying, that means we have to leave what we carry for a while. And the activation of fast sodium channels, the fast, okay, that's why it's called as the fast response over here. The fast response. That's where you see it's a shoots up. Okay, what happens? Activation of fast sodium channels. That's phase 0. Then we have phase 1, which is the rapid small depolarization, which is a half, like a semi depolarization. So that's phase 1. What happens over here? As I said, inactivation of the thing which we carried, which was the fast sodium channels. That guy has to stop. Then what happens? A flux of potassium, because it's repolarization. Repolarization, potassium. Depolarization, sodium, calcium, whatever it is. So over here, activation of potassium channels and the influx of chlorine, Cl minus. So that's this phase, the initial small repolarization. So over here we have what? The inward rectifying potassium channels. Over here we have the what? Fast sodium channels, and over here, which is the initial rapid partial repolarization. What happens over there? We have the activation of potassium channels and the influx of chlorine. So after that, we reach a phase called as phase 2, or else the plateau. What happens over here? In plateau, it maintains for a while. It maintains for around like 200 milliseconds, and the membrane potential over here is around the action potential over here is around 0. It's around the minimum, the nil position. So what happens over here? It's a balance. That's why it's a plateau. If something goes up, it has to have a deviation. So it follows a straight line. That means the thing which is coming in and the thing which is going out is in a balanced state. So we have the outward efflux of potassium with the help of delayed rectifying potassium channels, and the influx of what? Calcium and sodium. Calcium over here. So we have the efflux of potassium and the influx of calcium. With the help of, how does calcium come in? We have the long lasting, as we said over there, phase 0, long lasting, which comes over here in phase 2. So the long lasting calcium channels bring in the calcium, and the delayed rectifying potassium channels push out the potassium. So these both act somewhat similar and opposite. So it maintains a balance. We have one more thing, sodium calcium exchanger. It exchanges 1 calcium out for 3 sodium in, which means when 3 sodium comes in, 1 calcium moves out. So this helps in maintaining the potential of phase 2, which is plateau. Am I clear? Should I say it once again? What's plateau? Plateau means it has to have a balance of what? Something which is coming in. What's coming in? Calcium, with the help of long-lasting calcium channels. And what's going out? We have potassium, with the help of delayed rectifying potassium channels. Am I clear right now? Yes. Then we have the final step, which is phase 3. What's phase 3? What goes up has to come down. What's it? Repolarization, with the help of what? Delayed rectifying potassium channels again. Before that, which helped us to maintain the plateau, that guy has to shut down, or else what would happen? Repolarization wouldn't take place. So over here, what happens? Long-lasting calcium and sodium calcium exchanger has to give up. So what happens? The delayed rectifying potassium channels, which pushed out the potassium, has to stay for what? For repolarization to take place. So what happens over here? We have maximal activation of delayed rectifying potassium channels, and activation of inward rectifying potassium channels. Okay, this brings down the potential to the resting membrane potential, which was negative 90. Oh, it hurts. Oh my god. Next thing, we have something so-called action potential and mechanical response. Before that, we have a thing called as contraction and relaxation. What's contraction? Contraction of the heart. And what is relaxation? Relaxation of the heart. Okay, so let's look into it. As I said over here, depolarization stands for contraction. Repolarization stands for relaxation. I guess this is clear for everyone. If it's not, keep it in your mind. Contraction, depolarization. Relaxation, repolarization. So we have action potential and the mechanical response, which are relaxation and contraction over here. So think, this is the graph. This was the one which is said before, right now, which is the non-pacemaker cell potential, action potential. So think, what does this say? Contraction begins after the start of action potential. So look over here. This is where the contraction begins. This is where the action potential begins. So look, it begins after the initiation of what? I don't know. Of what? The action potential over there. So, and the maximum of what? The contraction happens at the end of the plateau, which is the phase 2, which is prolonged around 200 milliseconds. So that's contraction. What's contraction? It begins after the initiation of what? Cardiac myocyte action potential, and it reaches the maximum at the end of plateau, which is the phase 2. And we have something what contracts has relaxed. So relaxation, it begins in the first half of repolarization. Repolarization means relaxation. So which phase denotes repolarization? Phase 3. So relaxation begins in the first half of what? Phase 3. Now we have something so-called refractory period. What's refractory period? Over here we have two types of refractory period. We have absolute and we have relative. So what's absolute? Absolute refractory period is a period in which no matter how strong the stimulus is, the cells can't what initiate another contraction. So see, during the action, in absolute refractory period, a heart cannot re-excite. So no matter how strong what is the stimulus is, it can't generate another action potential, which means it can't excite. So what? Contraction won't happen. Next thing is relative, as the name suggests, relative refractory period. It's towards the late repolarization, as I said. Look over here. This is the repolarization. 1 minute. Let me tell you one thing. Absolute refractory period consists of which all phases? We have during the action potential and early repolarization. So think, we have the phase. What's this? Phase 0 and phase 1, phase 2. From phase 3, what happens? Relaxation happens. So in relative refractory period, what happens? What happens if we give a stimulus which is above the threshold? Supra threshold stimulus can cause a re-excitation of the cell. So that's what it says. The heart can be excited with stronger than normal stimulus, which means stronger than threshold, which is the supra-threshold stimulus. Am I clear? Now, what's the significance? What's the importance of refractory period over here? The first one is it prevents summation and tetanus. Think, heart is a pump, so it has to have its duration of contraction and relaxation. It can't stay contracted for a while, it can't stay relaxed for a while. So this refractory period helps in maintaining its pump activity. What am I supposed to say? Pump activity. It can't stay like contracted for a while. If it does, heart won't beat, we will die. So we don't want to die. So what happens over here? The significance of refractory period is to prevent summation and tetanus. Now, the resting membrane potential over here has, again, some factors which affects in maintaining it. First one, sodium potassium ATPase, which means it moves 3 sodium out for 1 potassium in. Next thing, we have the calcium ATPase, which means it pumps out calcium ATPase with the help of energy. So what happens? It pumps calcium out of the cardiac myocyte. Next thing, you have sodium calcium exchanger. It exchanges 3 sodiums for 1 calcium. So now one thing is that sodium calcium exchanger is a bidirectional pump, which means it can act in both directions. Depends on what? Depends on the electrochemical gradient. If something is inside and more, this guy will act on the opposite side to push it out. So if something is more outside, this guy will reverse and what it'll bring it in. So that's the thing, what? Sodium calcium exchanger over here. Next thing, okay, did I say that it moves in and out? No, it moves 3 sodium for 1 calcium. So it can be in either direction. If sodium is out and it's more, it will pump in sodium and push out 1 calcium. If sodium is in and it's more inside, it will push out 3 sodium and pull in 1 calcium. So that's what I said. It's a bidirectional pump. Am I clear? So the resting membrane potential, the ionic pumps which act to maintain it are 3: sodium potassium ATPase, calcium ATPase, and sodium calcium exchanger. Am I clear? Just 3. You will get the marks. If you just write these 3 names, you will get the mark. Next thing, okay, the important one: excitation, contraction, coupling. and inotropic state. What's inotropy? Inotropy is another name for contractility. The degree of contraction is another term for inotropy. No, inotropy is another term for the degree of contraction. Uh, so this is quite interesting, yet it could feel a bit intimidating because, see, look at this diagram. Whoa, 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 what's this? Damn. So, first thing, the membrane depolarizes with the help of what? What helps in that? I mean, see, once the membrane depolarizes, the action potential is generated, which moves along the what? Sarcolemma. What's sarcolemma? The membrane of what? The myocyte. So what happens? These action potential, which are the non-pacemaker action potentials. Okay, pacemaker is different. We are talking about contraction. So over here, what's involved? The muscle is involved. So what's this? The non-pacemaker action potential. It travels, and what happens over here? It reaches a thing called as L-type calcium channels, long type. So as the name says, it has to stand for a long time. So once the long type of calcium channels open, calcium enters in. Logic, calcium open, gates open, calcium go in. So what happens when the calcium enters? It reaches to a place called a sarcoplasmic reticulum. Whoa, fancy word, sarcoplasmic reticulum. What's sarcoplasmic reticulum? Sarcoplasmic reticulum is nothing but a pouch which stores calcium inside the muscle cell. So sarcoplasmic reticulum acts as a reservoir for what? Calcium. So once these calcium enter in with the help of what? Long type calcium channels, this guy reaches to a point called as RYR, ryanodine receptor. And what happens? It tells sarcoplasmic reticulum to push out more what? Calcium. So calcium come in, calcium attaches to the terminus cisternae, or another word is ryanodine receptor, and this triggers the sarcoplasmic reticulum to squeeze out, to push out more calcium into what? Into the muscle cell. So this is called as calcium induced, which means the calcium which came in from extracellular space to intracellular, triggering what? The sarcoplasmic reticulum to release more calcium. So that's calcium induced calcium release. So what induces the calcium from the outside? What releases sarcoplasmic reticulum? Both are calcium. So calcium induced calcium release. That's a fancy term for what? The action of calcium on sarcoplasmic reticulum to push out more calcium. So then what happens? The calcium which is present inside the cell goes attaches to troponin C, which will initiate contraction. That's another thing. That's another module. So calcium binding to troponin C induces contraction. That's the first part. So what contracts has to relax. What happens to relaxation? The end of action potential, which is this thing, has to go down. So when the action potential ends, the calcium release is decreased, and what happens? The calcium removal will take place. Now we have three major guys which helps in removing the calcium which we had inside before during contraction. Now the first thing is SERCA. What's SERCA? Fancy name. Sarcoendoplasmic reticulum calcium ATPase. Long term, short name SERCA. Okay, now see, this is SERCA. SERCA has a gate. It's a security. So what does security do? This guy doesn't allow someone to get inside. Okay, that's the purpose of security guard. So this security guard over here has fancy name, phospholambin. Phospholambin. So that's an inhibitory. So it inhibits the entry of calcium back to the sarcoendoplasmic reticulum. Okay, sarcoplasmic reticulum. Another short name. So what happens? We bribe this phospholambin. We phosphorylate this phospholamban and it opens. So what happens? The level of inhibition goes down. So the security who was a buff guy in the beginning becomes a soft guy, becomes a pookie. Okay, so this will help in the influx of calcium back to the sarcoplasmic reticulum. Am I clear? That's how Circa works. Circa pulls in the calcium which was given out by the same thing, but sarcoplasmic reticulum. That's the first thing. Next thing is sodium calcium exchanger. We discussed about it. What happens in sodium calcium exchanger? It pushes out one calcium for three sodium, which moves in over here because calcium is inside and it's in a huge amount. So we need to push out calcium, and we need to. So when a sodium calcium exchanger pushes out calcium, it brings in sodium. So that's the exchange. That's its work. We can't do anything. Next thing is calcium pump in sarcolemma, which means the membrane. So there's a pump called a calcium pump. So this pump helps in pushing out calcium along with what? Sodium calcium exchanger. Both of these guys pushes out calcium, but sodium calcium exchanger has another thing. It just brings in 3 sodium for 1 calcium it pushes out. And another thing, Circa. What's Circa? Sarcoendoplasmic reticulum, calcium, ATPase. If you write in a whole word, damn, the examiner might think, damn, this guy has brain. So the 3 things, Circa, sodium calcium exchanger, and calcium pump present in sarcolemma. And now the thing is the force of contraction, the inotropic state. I said the degree of contraction is another like set of words for what? Inotropy. Fancy name, inotropy. Simple name, simple words, force of contraction. Depends on calcium. Let me say, I am weak and I like chocolates. So I have to do something. Let's say I have a friend and he comes in and he asks me, can you do the assignment? I'll be like, no, bro, I'm tired. I can't do it. And he'll be like, I'll give you chocolate. I'll be like, nah, no, I don't want it. He'll be like, I'll give you 2 chocolates. I'll be like, okay, I'll consider. He'll be like, I'll give you 3 chocolates. I'll be like, sounds good. He'll be like, I'll buy whatever amount of chocolates you want. I'll be like, damn, I'll write whatever assignment he wants to. I might even finish this entire book. So the more calcium is provided to what? To the muscle cell, the more work it does. That means more, the degree of contraction is increased with more bribe he gets. The thing which he needs is calcium. So the more calcium, the more contraction. Simple logic. So that's state of what? Inotropy. Inotropic state or force of contraction. So that's this thing, excitation contraction coupling. Now we have another thing called as factors affecting inotropic state of the heart. So this guy, the inotropic state, also has something to control it. So what's it? Positive inotropy means stronger contraction. Negative inotropy means weaker contraction. Positive inotropy, we have the catecholamines or the sympathetic system, which releases norepinephrine, which is what? That's the neurotransmitter for this what? For the sympathetic system. So norepinephrine goes and attaches to beta-1 adrenergic receptor. So I'll tell you one thing. What happens in sympathetic system is that when the norepinephrine goes and attaches to beta-1 adrenergic system, a receptor, this guy says, okay, it's time to increase something to do the work. So what does it increase? It increases CAMP, cyclic AMP. So this will go and do the work on a thing called as protein kinase A, which will phosphorylate the what? Long type calcium channels. So what happens when long type calcium channels open for a long time? More calcium comes in. So that's the first thing. Then what? Calcium release channels on sarcoplasmic reticulum opens and more calcium is available for what? For the muscle cell to contract. So when the sympathetic system is doing the work, norepinephrine goes and attaches to its receptor, which is the beta-1 adrenergic receptor. Beta-1 receptor, leave it. Then what happens? It increases the CAMP, which does the work on a protein kinase A, PKA, phosphorylates PKA. Yeah, phosphorylates PKI, yes, yeah. Then what happens? It phosphorylates another thing. It's long type calcium channels. So this guy will bring in more calcium. Along with that, we have another thing: calcium release channels on what? The sarcoplasmic reticulum. Hmm? That will release more calcium. So these both are done with the help of sympathetic system. Next thing, glucagon hormone. We know insulin, glucagon. So glucagon, another way, increases CAMP. So CAMP does all this work, phosphorylates PKA, phosphorylates the long type calcium channels. So what happens? More calcium is available, and along with that, calcium release channels present over where? So sarcoplasmic reticulum. So both these does the work. More calcium is available for the cell to do the work, which is contraction. Next thing, increasing the extracellular fluid calcium concentration, which means the amount of sodium outside the cell is more. So what does that mean? More calcium is available for the cell to bring in. So what happens? Which increases the calcium entry. Increased ECF calcium concentration increases the calcium entry. So that's another thing. So sympathetic, glucagon, and ECF, increase in ECF calcium concentration. Now we have drugs, the medicines. Digitalis, an important drug. What happens? This guy inhibits sodium potassium ATPase. What happens? Now think. Sodium potassium ATPase has to bring in sodium, right? Push out the sodium. So what happens when we inhibit sodium potassium ATPase? The sodium that moves out of the cell is blocked. The moving out process is blocked. So what means intracellular sodium concentration is increased markedly as compared to when this guy, which guy? Sodium potassium ATPase does the work. Digitalis goes and inhibits sodium potassium ATPase. So what happens? This sodium potassium ATPase stops working, means it stops pushing out sodium. So the sodium which is inside the cell increases. Now we have another guy. What was it? Sodium calcium exchanger. This guy has to move out 3 sodium, right? So what happens? As I said, this is a bidirectional pump. So what's inside and what's more? Sodium is inside and sodium is more. So this guy activates. This guy starts to work. This guy pushes out 3 sodium and brings in 1 calcium. So what happens over here? Calcium inside the cell is increased. So what happens? More calcium, more work. Positive inotropy. Am I clear? Should I say it once again? Digitalis inhibits sodium potassium ATPase, which increases the intracellular concentration of sodium. So what happens? Sodium calcium exchanger has more sodium to push out. So when it pushes out more sodium, it brings in calcium, which means intracellular calcium is increased. So what happens? Contraction is increased, which means positive inotropic state. Next thing, we have xanthine. What's xanthine? Caffeine. It's a part of xanthine. It's another guy. It's xanthine is a family. Caffeine is a member of the family. So what happens? Xanthine increases CAMP. So what happens? What happens when CAMP is increased? It goes to PKA. PKA helps in phosphorylation of what? Long type calcium channel. It opens for a long time. Calcium comes in. More calcium comes in. What happens? More calcium inside. More the degree of contraction, which means positive inotropy. Am I clear? That's positive inotropy. So we have sympathetic, glucagon, increasing in extracellular fluid, and drugs, which are digitalis and xanthines. Now we have negative inotropy. So which means it has to go through a weaker state of inotropy. Weaker one. So the force of contraction is less. What happens over here? We have the vagus system, which is the parasympathetic system. So what is the neurotransmitter of parasympathetic system? It's acetylcholine. So this guy goes and attaches to its receptor, which is the muscarinic receptor, which decreases CAMP. Sympathetic increases CAMP, parasympathetic decreases CAMP. Now, what if CMP is decreased? All the steps which we discussed just a while ago goes down. What? L type won't be open for a while, so the amount of calcium that's coming in is way less than the sympathetic system, so the contraction is less. Negative inotropy. Next thing, adenosine. Adenosine over there, which we discussed about glucagon. Glucagon increases CMP. Opposite to that, we have adenosine, which decreases CMP. The rest of the steps are the same. Hypoxia of myocyte. Hypoxia, ATP. ATP is required for what? So, ATP is important for this guy. What? For the contraction. Contraction, ATP is required. So if the ATP is less, contraction would be less. Contraction won't happen to that degree of extent. So what happens? Weaker contraction, negative inotropy. Now we have drugs. CCB, calcium channel blockers. What happens? Calcium channel blockers inhibit L-type calcium channel. So it decreases the amount of calcium that comes into the cell, which means, again, weaker contraction, negative inotropy. Another one is anesthetic drugs. Just memorize it, anesthetic drugs. That's it. So we have vagus, adenosine, hypoxia, and the drugs, CCB and anesthetics. Over there, the drugs were xanthines and digitalis. Vagus, negative. Sympathetic, positive inotropy. Adenosine, negative inotropy, decreases CAMP. Glucagon over there, increases inotropy, increases CAMP. Hypoxia, decreases ADP, and the drugs. I guess that's clear. Oh my god, the biggest one, the big guy, cardiac cycle. Now this is a bit big, huge. So focus. What's cardiac cycle? It's the period during which the heart completes one contraction and one relaxation, which in fancy term means one systole and one diastole. So we have a thing called ECG. Very fancy diagram. Everyone has seen it. So what does it say? ECG has a bunch of curves, right? This is the P, Q, R, S, and the T wave. So what happens? Initiation of P wave by the ECG, of the ECG, and so this marks the beginning of what? The cardiac cycle, the contraction, the systole. And what happens in QRS? That's another case. We'll discuss about it later on. So is this cardiac cycle? So this along with the next initiation of the contraction. So the gap between, this, the period between two successive P waves. P waves are, is called as the cardiac cycle. So duration is around 0.8 seconds. How do we get it? 1 minute is 60 seconds. 1 minute is 60 seconds, and an average heart rate of normal human being is 75 beats per minute. So if you divide 60 by 75, you get 0.8 seconds. So that's the duration of one cardiac cycle, which means one set of systole and diastole. Now we have the timing. So atrial systole means the atria has to contract. That's just 0.1 seconds out of 0.1 second out of the whole 0.8 second cycle. Now our atrial, did I say arterial systole? It's atrial systole and atrial diastole takes the rest 0.7 seconds. Okay, which means the atria has nothing to do for the what? The rest 0.7 seconds. Okay, before that, we have phases. We like phases. We discuss about the phase. We discussed in pacemaker potential, non-pacemaker potential, and now we have the cardiac cycle. This cardiac cycle is divided into 7 phases. So the first phase is atrial systole, which we discussed. Then we have the remaining 6 phases. So 6 phases means the atria is in a relaxed state. Now we have the ventricular systole, which is around 0.3 seconds. The ventricle has to do the work. It has to push out the blood from the ventricle. It has to push. It has. I mean, I guess my hair is making a bit too noisy. It's a bit too noisy. Yeah. So the ventricle has to push out the blood from a place which is below to a place which is above. So it has to push out the blood to the pulmonary trunk and the aorta. So it has to do a bit more work for a longer duration. So it stays from 0.1 to 0.4 seconds. Now the phases, okay, the ventricular systole has 3 phases: phase 2, phase 3, and phase 4. We'll discuss about all these phases in the next slide. So just stay with me. Then we have the ventricular diastole, which means the ventricle has to relax. That's for another 0.5 seconds. So it's from 0.4 to 0.8, plus the one which coincides with the next atrial systole. So that's the next 0.1 second, the time, because 0.4 to 0.8 is 0.4 seconds duration. So what we wrote 0.5, which means it overlaps with the atrial systole in the next cardiac cycle. It's a very intertwined cycle, so stay with me. So it has 4 phases. If ventricular systole has 3 phases, which were 2, 3, and 4, over here ventricular diastole has 4 phases: 5, 6, 7, and 1. We don't have 8, we have 7 plus 1, which is the atrial systole. Now the key relationships, I'll just read it. Atria and ventricle do not normally contract at the same time. Why? The blood has to move. If both contract at the same time, the blood won't move. It has to create a pressure gradient from the above region to the below region. So the atria contracts, then the ventricle contracts. If both atria and ventricle contracts together, blood will not move. Next thing, atria and ventricle relaxes together. So what? It doesn't contract together, but it relaxes together for 0.4 seconds. Over here, ventricular diastole, which coincides with atrial diastole. Now, atrial systole coincides with what? The last 0.1 seconds of ventricular diastole. That's what I mentioned over here. 0.1, 0.1. Atrial systole coincides with ventricular diastole. That's called as late diastole, because the diastole is prolonged a bit more than the normal cycle duration, which is 0.8. Next thing is the effect of heart rate on the duration. So increasing in heart rate shortens the diastole. It affects the diastole more than it affects the systole. So what happens? The cycle shortens, because think, diastole has the most duration in this cycle. So because atrial systole was 0.1, ventricular systole was 0.3, and ventricular diastole was 0.5. So the one which has the most duration is shortened. That means the whole time will be shortened. The whole duration would be shortened. That's what it's said over here. Next thing, if the heart rate is an average heart rate of 75 beats per minute, the cycle is for 0.8 seconds, and systole would be 0.3 seconds, diastole would be 0.4 seconds. If the heart rate is increased, which means tachycardia. What's tachycardia? A state in which the heart rate is increased. What's bradycardia? A state in which the heart rate is decreased. So in tachycardia, what happens? the cycle, the duration of the whole cycle is reduced to 0.3. So in a normal rate, it was supposed to be 0.8, but in a short, in a rate, in a state where the heart beats fast, the cycle duration is decreased to 0.3. So the systole would be 0.15 seconds long, and the diastole would be 0.15 seconds long again. So 0.15 plus 0.15 is 0.3. Maths. Now let's talk about the phases, which we said a few minutes ago, which was what the cardiac cycle is divided into 7 phases. 1, 2, 3, and 4. We have the rest 3 coming. Patience. The first phase, atrial systole, which coincides with the ventricular diastole, isn't it? The 0.1, remember? So, atrial systole, the duration is 0.1 seconds, evacuates just 20% of the blood. So, the rest 80%, who does the work? It is done by the gravity along with the pressure gradient. So, think atria is over here, ventricle is over here, and there's a valve in between. If the valve opens, gravity will pull the blood down, which accounts for the 80% of the work which is done, and the rest 20 is done by atria. Okay, then the ventricular volume is increased to end diastolic volume, which means the volume which the ventricle has at the end of relaxation, because when it relaxes it can hold blood. So the maximum amount of blood which is present in the ventricle after diastole, after relaxation, is called as the end diastolic volume. Okay, so during atrial systole, the ventricular volume is increased to EDD. Then the left ventricular pressure, because what happens in left? Oh, wait. Okay, it is increased 0.9 millimeter. So the pressure is increased. AV valves, are they open? They are open because it has to push out the blood. So the AV valve is open. What semilunar valve? Semilunar valve, let's talk about the right side. So the semilunar valve which pushes, through which the ventricle pushes the blood to the pulmonary trunk is closed, because if it's open, then we would go to the next phase, which is not we are talking about, which is not the thing which we are talking about. So the semilunar valves are closed. Semilunar valves are closed, but the AV valves open. Then we have the aortic pressure. It is decreased as the blood flows to the periphery. Why? Let me see. It's an interesting thing. So we have the veins which brings in the blood, and we have the aorta, which we are talking about. Aorta, aortic pressure. The valve over here is closed, which is the semilunar valve, but there is blood over here inside, and the blood is moved towards the periphery. So what happens to the pressure over here? It's decreased. If the blood stays over there, then it would remain as the same. Or else, when the blood moves out of a closed compartment, the pressure inside the closed compartment decreases. That's what it's written over here. It decreases the aortic pressure, not the atria. It's the aortic pressure decreases as the blood flows to the periphery. Then we have the atrial pressure. It's not the aortic, it's the atria. It causes a positive A wave. Because why? Because the atria is contracting. So the contraction means there has to be an increase in the pressure, because there is something inside. Now the atrial depolarization, or the atrial systole contraction, coincides with what? The P wave in the ECG. Remember, I drew the ECG over here, the P wave. This is atrial systole. Now the next phase, phase 2, which is the isovolumetric contraction. What's isovolumetric contraction? Iso means the same, volume, volume. So the volume is not changed during this phase. So the contraction happens, but both the gates, which are the AV and semilunar valve, are closed. So the volume, the blood's neither moving out nor coming in, so the volume is constant. Hmm? So this accounts for 0.05 seconds of what? The whole cardiac cycle. Oh, let me tell you one thing. This entire thing is ventricular systole. Okay? So that's what we said over here in C. Ventricular systole consists of three phases: 2, 3, and 4. 2, 3, and 4. So ventricular systole. So what happens in the beginning of ventricular systole? There's a phase called as isovolumetric contraction, phase 2. Over here, the blood volume is not changed, yet the pressure is changed. So the ventricular volume is constant. The ventricular pressure is rapidly increased to 80 millimeters of mercury. So during this phase, what happens? The pressure is increased because it's contracting. Now, what happens over here during isovolumetric contraction? There has to be a sudden closure of what? The gate, which was above, which brought in the blood, which was AV valves. Atrioventricular valves. So that has to close, which makes the first heart sound, the lub of the thing which I have been like learning from, I don't know, for a while. Lub dub, lub dub, lub dub. The lub is the closure of which valve? AV valve. So that's the first heart sound, which is also called as S1. Now what happens over here? Which is closed over here? Semilunar valve, because the both gate has to be closed for the volume to be constant. Now aortic pressure reaches to a minimum. Okay, why? Because again the valve of aorta, which is a semilunar valve, is closed, so nothing goes in. So what was remaining inside the aorta moves out to the periphery. It goes to circulation, systemic circulation. So the pressure decreases. Now we have a thing called as dicrotic notch. What's dicrotic notch? When the pressure varies, the pressure graph of this gives a notch. It gives a hook. That's called as dicrotic notch. And after that, we have a thing called dicrotic wave. I'll talk about it later. But yeah, dicrotic notch is due to what? The movement of blood from the aorta to the periphery. So decrease in the pressure creates the dicrotic notch. Am I clear? Then we have the atrial pressure. What's atrial pressure? Atrial pressure gives a positive C waves. Now think why. Again, it's a bit too complicated, so let me tell you. This is ventricle. This is aorta. Atria, and we have a gate. Let me change the color. We have a gate over here. This gate was closed when during isovolumetric contraction. So what happens when this contracts? The volume inside will exert a pressure on the mobile parts. AV valve is a mobile part. It moves. So when it exerts a pressure, this valve moves upwards. So it creates a pressure, a slight pressure difference, an increase, where in the pressure of what? Atria. So that's why it gives a tiny C wave. Cause why? It's because the bulging of AV cusp, the leaflets. Now it coincides with the QRS complex. QRS means ventricular systole, depolarization. So systole, yeah. So that's isovolumetric contraction. Again, it is just a tiny portion of the cardiac cycle, 0.05 seconds. So what happens over here? The pressure is constant, but the ventricular pressure is increased. Then what happens? Sudden closure of the AV valves gives the first heart sound, S1, the lub. What happens? Semilunar valves are closed because isovolumetric. Nothing should come in, nothing should go out. The aortic pressure decreases to a minimum because the semilunar valves are closed. So what happens? The blood inside the closed aorta moves out. So the pressure inside the aorta is decreased to the minimum. Then we have the atrial pressure. Why? Because the bulge of AV cusp. So it creates a C wave. Then the ECG, it coincides with the QRS complex. Now we have a thing called as rapid ejection. So once the pressure, see, think my mouth as the ventricle. So, so what happens when I close my mouth and I push in air? So what happens? The pressure is increased, yet nothing is going out. So when I suddenly release my hand, the pressure, I mean the air has a gap to move, so it gushes out. So that's rapid ejection, the ejection of blood in case of the heart, air in case of the mouth. Okay, so this accounts for 0.1 seconds of this whole phase. I mean whole cycle. And what happens? There's a rapid decrease of what volume of the blood volume in the ventricle, because it pushes out to whatever it's above. If it's left, it pushes to the pulmonary trunk. If it's right, it pushes to the aorta. Then what happens? The left ventricle, the pressure is increased to the maximum. I mean, not maximum. Yeah, I guess the maximum. Yeah, it's the maximum. So it's 120 millimeters of mercury. The pressure is increased. Then what happens? Which valve has to be closed over here? The AV valve has to be closed. Why? If the AV valve was open, what happens? The blood would go back to the atria. We don't want that. We want the blood to go to the other side, to the whatever it supplies to, lungs or the systemic circulation. So what has to open over here? Semilunar valves have to open over here, because we have to push out the blood to our like destination, which is either lungs or the systemic circulation. Now think aortic pressure. So yeah, that's okay. That's what it's written over here. It's left. So consider. I mean, in the previous phases, the semilunar valve was closed. So what happened? The pressure of the aorta was decreasing because the blood inside the aorta was moving out. Right now, the semilunar was opened with a left ventricular pressure of 120 millimeter of mercury. So this pressure radiates to the aorta. So the pressure inside the aorta becomes 120. So it increases to 120. Am I clear? Then the atrial pressure. What's atrial pressure? The pressure inside the atria gives a negative X wave. Why? Because due to the pulling of AV ring. So let's say this is the ring and this is the ring and this was the cusp. So when the ventricle, this is the ventricle. I don't have four hands. So this is the ventricle, this is the atria, and in between we had the what? We had the AV valve, the cusp and the ring. So when the ventricle contracted, this bulged, this gave a bulge. So what happened? It created the C wave in the atrial pressure. So now think, the blood inside over here moves to somewhere, so it creates negative pressure over here. So it pulls the AV ring, the whole cusp and the ring. So it creates a negative pressure inside what? Atria. So it gives the negative X wave. And at the same time, we have the venous return coming in to the atria, so it increases as well. So it decreases along with the pushing out, the gush of blood to let's talk about the left side, to the aorta. But we have the venous return coming in. So what happens over here? It is increasing. The pressure of the atria is increasing. Now the ECG, don't bother about it. So the next phase, the reduced ejection phase. So what happens over here? We have the rapid ejection. So as the rapid ejection continues, the blood volume inside decreases. So the amount of ejected material, which is the blood, is decreased. So that's why it's called as the reduced ejection phase. Now this is, this is shorter. It's 0.15 seconds. So what happens over here? The blood volume decreases to what? End systolic volume. What's end systolic volume? End systolic volume is the amount of blood present inside the ventricle at the end of its systole. So after contraction, the amount of blood which is remaining in the ventricle is the end systolic volume. So during reduced ejection phase, the volume is decreased, but it remains, it holds back to a little amount of blood. So that's the end systolic volume. Now, what happens over here? The pressure of the left ventricle is decreased. Why? The momentum of the blood, the momentum with which the blood moved from the ventricle to wherever it was going is continued. So the momentum pulls out the blood. So what happens? The pressure is decreased. What happens over here? Again, we are in the ventricular systole. So what has to be closed? The AV valve has to be closed. What has to be opened? The ventricle is contracting, so it has to push the blood to wherever it's supposed to push. So the semilunar valve has to be open. It has to be kept open throughout this whole phase. Then we have the aortic pressure. We have the dicrotic notch. What's dicrotic notch? Dicrotic notch is the it's the near end of dicrotic notch. I'm so sorry. It's towards the end of dicrotic notch. Okay. The reduced ejection coincides with the end of dicrotic notch. Now we have the atrial pressure. Atrial pressure creates a positive V wave. Why? Because the venous return, venous return comes to the atria. So what's coming? The blood is coming. So it's getting accumulated inside the atria. So it pushes onto its walls, which gives an increase in atrial pressure. And we have the ECG, which coincides or which denotes the beginning of T wave. What's T wave? T wave is ventricular repolarization. Okay, so I guess, is it fine? It is a systole, ventricular systole, which are isovolumetric contraction, rapid ejection, and reduced ejection. Okay, all these four phases, the first part. Now let's come to the next part. We have ventricular diastole. Ventricular diastole. This chair. Ventricular diastole is divided into three phases, but over there we discussed another phase which coincides with phase 1. Leave it. Over here we have the isovolumetric relaxation. So again, isovolumetric means the volume doesn't change. So both the gates, which are the AV and the semilunar, has to be closed. Over here we get the second heart sound. I'll talk about it. Wait. So the duration of this phase, which is the phase 5, 6, and 7. Phase 5 is for 0.1 seconds. And what happens over here is volumetric relaxation. So the ventricular volume is constant. Ventricular pressure is decreased. It's obviously decreased because the blood moved out. Then what happens? AV valve closes. The sudden closure of AV valve no, it's closed. Semilunar valve. The semilunar valve has to close over here. That's why we get the second heart sound, which is S2, which is, in fancy words, the dub. So the lub is S1 and the dub is S2. S2 is is made due to the closure of semilunar valves. This is wrong. Then we have the aortic pressure, the pressure inside the aorta. It has a small increase, the dicrotic wave. Why? Think. What closed over here? The semilunar valves closed over here. So the blood was moving out of the ventricle to the aorta and the semilunar valve closed. So what happens? The blood which moved out comes back, hits the aorta, gives what? A bounce. This bounce creates something called so-called a dicrotic notch. Am I clear? So it has a small increase and then a small decrease. So a tiny increase and a tiny decrease. That's the dicrotic wave. Okay, that's aortic pressure. So what's dicrotic wave? It's the bouncing back of blood on the closed semilunar valve. Then we have the atrial pressure, again positive V wave due to the accumulation of blood, the venous return. Heart sound, we have the second heart sound which was dubbed due to the closure of semilunar valves. Then we have the sixth phase, rapid filling phase, which accounts for another 0.1 second. What happens over here? The ventricular volume is increased rapidly. As the name says, rapid filling. The volume is increased rapidly. 80% of the blood flows in passively. Why? Gravity and the pressure gradient from the difference between what? Atria and the ventricle. Now the ventricular pressure. What happens over here? Decreases the ventricle, relaxes to. Oh yeah. So what happens? Blood has to come in, so the ventricle relaxes. It contracted, now it relaxes. So what? The pressure is slowly decreased to accommodate the blood which comes in to the ventricle. So then it increases. Why? As we, let's say, uh, um, yeah, let's say I'm pouring my I'm like cupping my hands, I'm pouring water into it. So during the initial phase, what happens? The pressure is low because I'm accommodating for the increase of, oh, you can't see, so for the increase of volume that's coming into my hand. But later on I can't increase further more than this, so I had to keep it closed. So the further increase in volume increases the pressure. So that's the logic behind it. So it decreases as the ventricle relaxes, but then it increases because the volume, the amount of stretchability, the amount of what capacity it can hold is constant, but the volume keeps on coming in. So the pressure increases inside the ventricle. What happens to the AV valve? The AV valve is opened. Why? It has to bring in blood. That is rapid filling. For the rapid filling to take place, the AV valve has to open. The opening of AV valve is due to what? It's due to the increased atrial pressure as compared to the ventricular pressure, because the blood inside the atria was increased due to the venous return, and then the what opens, the AV valve opens, and the ventricle receives the blood. Semilunar valve has to be closed because if it's open, that's a different phase. Aortic pressure decreases as the word, because the blood is moved to the periphery. The same thing which I talked about for a while ago. Then we have the atrial pressure. It creates a negative Y wave. Because why? Because the blood moves from the atria to the ventricle during the rapid filling phase. Then we have S3 over here. This was S2. S3 is due to the rapid blood flow to the ventricle. So when the blood gushes out from the atria to the ventricle, it hits on the walls of ventricle and it creates S3. Now we have the reduced, the last, my throat, the last filling phase. What is it? The reduced filling phase. Over here, it takes around 0.2 seconds. And what's over here? The ventricular volume is increased but slowly, because reduced filling phase, the volume which comes into the ventricle is less. Then the ventricular pressure is increased by a bit, little increase. Then the AV valve has to be open because blood has to flow from the atria to the ventricle. Semilunar valve has to be closed. Aortic pressure, because what? The blood keeps on moving. Then the atrial pressure, a tiny rise. Why? We have the venous return coming in. Heart sound, no heart sound is made over here because the heart sound which was supposed to be made was made in the previous phase, which was the rapid ejection and filling phase. Okay. Oh my god. Then we have the cardiac output and performance. So what's cardiac output? Cardiac output is the amount, the blood that's pushed out by the heart in one cycle. Let's say. Cardiac output, we have the key volumes which we have to know over here. We discussed about the end diastolic volume, which was the amount of blood which was remained in the ventricle at the end of diastole, the end of relaxation, the collected blood, the total collected blood. End systolic volume, that's the amount of blood which was inside the ventricle after the contraction. So once the ventricle pushes out the blood, it has to, a little amount of blood remains in the ventricle. That's called as end systolic volume. Then we have the stroke volume. Stroke means per beat. Yeah, so the volume of blood that's pumped out by the ventricle per beat is end systolic. Stroke volume. So what's stroke volume? The equation for stroke volume is stroke volume is equal to end diastolic volume minus end systolic volume. Then we have the cardiac output. Just give me a minute. Let me just drink better. Stay hydrated, people. Stay hydrated. Now we come to the major part, the cardiac output. What's cardiac output? It's the volume of blood pumped. Oh, sorry. It was the volume of blood which was pumped out by the ventricle in each minute, per minute. Okay, that's cardiac output. Stroke volume is different. Stroke volume was per beat. Cardiac output is per minute. Okay. Then we have another equation for what? For cardiac output. It is heart rate times stroke volume. So I can write it in a different way. This is going to come handy when you solve numericals. I wish nothing comes up, but if it comes up. So what? Cardiac output is heart rate times, we're going to substitute stroke volume for end diastolic volume minus end systolic volume. This is another form. Keep this in mind. It might come in handy. It might come handy, yeah. Now we have something so-called cardiac index. There was a question, I don't remember. There was a question, I don't know, in some MCQ, PYQ, which is cardiac output and cardiac index the same? No, it's not the same. Cardiac index is cardiac output upon body surface area, the BMI. Body surface area. So the thing would go as 3.2 liter per minute per area, meter square of what? The body surface area. So this is an important thing. I don't know. I don't think it's going to come up for this exam. But yeah, if it comes up, keep this in mind. Cardiac index and cardiac output are not the same. So we have a thing called ejection fraction. What's ejection fraction? Ejection fraction is the amount of blood or the fraction of blood that's ejected during the contraction of what? The ventricle. So it's clinically used as an index of contractility. So what was contractility? Contractility is the degree of contraction. Yeah, right? The inotropy. So increase in inotropy will push out more blood from what? The blood it had. The blood the ventricle had, it pushes out more blood when we have more degree of contraction. So increasing inotropy increases the ejection fraction. Now, ejection fraction, the equation for ejection fraction is stroke volume divided by end diastolic volume. The end diastolic volume was the volume which the ventricle had, and stroke volume was the volume of blood that ventricle pushed. So the amount of blood pushed by the amount of blood it had gives the fraction of the amount which was ejected. Okay, and it has to be above greater than 55 percentage. So if it's less, it means there's some issue with the heart. So decreased ejection fraction means indicates heart failure or something with the heart, some issue with the heart, which affects its contraction, which affects inotropy. Now, cardiac output in various conditions. This is just facts. In exercise, it increases by 700%. Excitement, anxiety, 100%. Eating, 30%. High temperature, pregnancy, all this increases the cardiac output. Decreases rapid arrhythmia because the heart doesn't have time to fill up. Standing from supine because the gravity, it pulls. Heart failure. Heart failure, heart has failed because because I don't know, some reason. So what happens? The heart can't push the blood. So the cardiac output is decreased in case of heart failure. Now we have the control of cardiac output. What was the equation of cardiac output? Heart rate, stroke volume. So what affects this thing? The heart rate, the cardiac output, heart rate and stroke volume. So heart rate plus stroke volume, isn't it? So stroke volume is affected by preload, afterload and entropy. What's preload? Preload is the amount of blood that comes in the venous return. What's afterload? Afterload is the resistance offered by the vessel when the heart pushes out the blood. What's inotropy? Inotropy means the degree of contraction, the contractility. Okay, so these three affects the stroke volume. So if preload is increased, the stroke volume will increase. If the afterload is decreased, the stroke volume will increase. If the afterload is increased, the stroke volume will decrease. It's inversely proportional. Okay, and if the inotropy is increased, stroke volume will increase. We're going to discuss about that over here. The effect of heart rate on cardiac output. Change in heart rate, it's quantitative more than qualitative. Think, while an untrained person is doing some sort of physical exercise, what happens? Our body needs blood. So what happens? The heart rate will increase around 100 to 200%. But what happens? The stroke volume does not increase proportionally as compared to like other trained athletes. So what happens? There is just a slight increase of stroke volume, cardiac output over here, which is less than 50%. So is there an increase? Yes, there is an increase. But is there a drastic, huge increase? No, it's just less than 50%. Now, doubling of heart rate. So let's say if heart rate was X, doubling to X would give no much change in cardiac output, because think, see, when does doubling happen? It happens in artificial pacemaker and arrhythmia. Arrhythmia, that's a case in which the heart's contraction, the discharge, the rate of discharge is affected. So the rhythmicity is compromised in arrhythmia. Okay, so talking about it, increasing in heart rate decreases the stroke volume to half because the ventricle doesn't have enough time to collect the blood. Didn't I say that diastole becomes short and it's affected the most when the heart rate is increased? So what happens? Decreasing diastole time, thus decrease in filling. So what happens? Now think, when the heart rate is above 150, tachycardia, the cardiac output is decreased. Why? The increasing heart rate cannot compensate for the decreasing stroke volume because the time is less for the ventricle to collect blood. Next case, when the heart rate is below 60, means bradycardia. Again, the cardiac output is decreased. Why? The stroke volume cannot compensate for the decreased heart rate. So think, the volume which comes into the ventricle has its limit. Due to what? Due to the ventricular capacity. As I said, my cupped hands, it can't go beyond this. I can't stretch. I just have a limited tiny volume which can be, in my hands. So next thing is during exercise. Normal physiology. Doubling heart rate doubles the cardiac output. Over here, why? Due to increased stroke volume by different physiological mechanisms. There are a bunch of physiological mechanisms that helps in increasing the stroke volume. Could be like decreasing the afterload, increasing the preload, increasing the heart rate. I will talk about it. Sympathetic stimulation. So as I said, we discussed about sympathetic stimulation gives tachycardia. Hmm. So increasing heart rate. Positive inotropy. Then I say the beta 1 receptors are affected. So what happens? The CAMP increases. So that's it. Now we have increased venous return, thus increasing the preload. So what happens? Frank-Starling mechanism. When the preload is increased, the amount of stretch, contraction, the inotropy is increased. So what happens? The cardiac output is increased. Now result, cardiac output can increase up to 7% in trained athletes. But if it's a normal untrained person doing the exercise, there is no further, there's no drastic change in the stroke volume. Okay, but over here, cardiac output in a trained athlete can reach up to 700%. That's a huge number. Okay, very fancy curve. This might come. I don't know. Some sort of like Spider-Man thing. So I have the sense, spider sense. So the pressure volume loop. What's the definition? The definition of pressure volume loop is the change of ventricular pressure. Over here, we are discussing about the ventricular pressure in relation to change in ventricular volume. So the pressure and volume of the ventricle is being discussed over here. The width of stroke volume loop, which means, pressure volume loop. So that means this, the gap. This is the volume, right? So this gap, this width gives the stroke volume. Let's say from x to x1. So the x1, when we subtract x from x1, we get the stroke volume. The area, the whole thing over here, gives what? The stroke work. That means the stroke volume multiplied by the mean aortic pressure, the afterload. So the volume against the resistance, the work it has to do can be calculated by figuring out the area which is enclosed in this pressure volume loop. Now we have something so called end diastolic pressure volume relationship. Think, what's diastole? Diastole means it was relaxing. So it's a passive length tension relationship of isolated cardiac muscle. That's a different topic. I don't think it's included for your exam. So yeah, passive length tension relationship of an isolated cardiac muscle. So it's a passive process. So end diastolic pressure volume relationship. This guy over here, the tiny dotted line, the long dotted line, is the end diastolic pressure volume relationship. So increasing EDV increases the end diastolic pressure. It's clear from over here. You can see. This is the EDV, the increase in volume. See, at point C we have the EDV. So when the EDV is increased, when the volume is increased, the pressure is also increased, but to a slight extent. Then what happens? We have something called end systolic pressure volume relationship, which is over here because during systole the pressure is high. It's an active length tension relationship. Slope depends on the inotropic state. We'll discuss about it in a minute. So when the inotropy is increased, the slope will increase. Starling law, within limits, the end diastolic volume gives the maximum end systolic pressure. That means the greater the amount of stretch, the greater the amount of contractility. Now we have the loop points. This is point 1, point 2, point 3, and point 4. So what's point 1? In point 1, we have the end systolic volume. That means the mitral valve has to close. So when the mitral valve closes, what happens? The mitral valve opens. That means the AV valve is open over there. So what happens? The blood flows from the atria to the ventricle, and what happens? The ventricular pressure is kind of increased slowly. And the volume is also increased when it goes like this. So at this point, the ventricle has the maximum amount of blood, which is the end diastolic volume, because the ventricle relaxed to accommodate all those blood coming from the atria. So once it reaches over here, the phase which begins over here is called isovolumetric contraction, because the volume as we move up doesn't change. So what happens over here, the mitral valve has to close, and when it closes, the contraction of the ventricle gives the isovolumetric contraction. So at point D, what happens, the pressure exceeds the aorta. So what happens, the aortic valve opens and the blood gushes out to the aorta from the ventricle. So that's this. The volume decreases. This is the rapid ejection. This is the rapid ejection phase. And over here we have the reduced ejection phase. So at point F, what happens? The pressure gradient is different and the aortic valve closes, isn't it? Now, that's what these lines say. Lines 1 to 2. The filling phase, the volume and the pressure is increased. Line 2 to 3, the line which goes like this, it is the isovolumetric contraction phase. So we have the constant volume, but we have an increase in pressure. Now 3 to 4, it's the ejection. So the first part of ejection is rapid ejection over here and the reduced ejection. So what happens? The volume is decreased, the pressure is increased, then it decreases slowly. Point 4, the line 4 to 1 means isovolumetric relaxation, means the ventricle is getting prepared to accommodate, to receive the blood that's coming. So over here, what happens? Mitral valve is open, mitral valve is closed. In other words, AV valve is open, AV valve is closed, aortic valve is open, aortic valve is closed. So that's it. Then this is filling, a word of the ventricle. This is isovolumetric contraction of what? The ventricle. What's this? Ejection of what? The ventricle. What's this? Isovolumetric relaxation of what? The ventricle. So over here, we are just bothered about the ventricle. Okay. I think we are about to be, we are kind of done. Just 6 more pages. Now we have the effect on stroke volume and pressure volume loop. Increasing the preload, which means increasing the venous return, EDV. The preload is the degree of stretching of myocyte sarcomere before the contraction. That means the more EDV, the more it stretches, right? Before it starts to contract. EDV depends on the venous return via what? The major veins. We have superior vena cava and the inferior vena cava. Increasing in preload increases the stroke volume. What was it? The Starling's law, the Frank-Starling's law. It has a fancy name, heterometric autoregulation. So increasing in preload increases the stroke volume. Easy. In PV loop, increasing in preload increases the volume along the what? EDPVR line, which was the end diastolic. So increasing the preload shift. Wait, let me just clear this. So what happens over here? Think. When we increase the stroke volume, this point, the end diastolic volume is further increased. It reaches over here. And what happens? What does it say? The contraction begins at higher EDV. So the contraction begins at over here. Reaches the same ESV. So it has to reach back the same end systolic volume. So what happens? The stroke volume is, oh my god. It was over here. The stroke volume is increased in case of increased venous return. Am I clear about what I said over here? When the venous return increases, the end diastolic volume is increased because the more amount of blood is reaching the ventricle. So what happens? The contraction begins to reach where? To the our normal ESV, end systolic volume. So what happens? The degree of contraction would be high. So what happens? It increases stroke volume. Factors affecting the preload. What is it? Increased venous return increases the preload, increases the amount of blood that comes to to the what ventricle, aorta, wherever it is. Strong atrial contraction. When the atria contracts to a greater strength, the greater amount of blood is being pushed where to the ventricle. Increased heart rate decreases diastolic time, decreases preload activity. So what? Preload is decreased by increasing in heart rate because diastolic time is decreased, as I said before. Factors affecting negative preload. What happens over here? Ventricular decreased ventricular compliance. If the ventricle can't receive an increased amount of blood, then what happens? The preload is decreased. What are the conditions? Myocardial infarction, which means the death of the myocardium. So it can't function properly. The muscles. So what happens? The amount of blood which it can accommodate is compromised. Hypertrophy. Hypertrophy means the increase in the size of the muscle. So what happens? Think, if I increase the width of the muscle, the ventricle becomes, the volume inside the ventricle is kinda lower than the normal condition. So what happens over here? Compliance is reduced. So what happens over here? Now think, if the EDVPR is, the slope is increased, which means the pressure is increased, thus the volume would be compromised, which means there is a negative preload in case of increasing in the slope of. Let's put it the other way. If there is a decrease in preload, the EDVPR, the end diastolic volume pressure volume relationship, the curve will have an increased slope. Okay. Effect of afterload and inotropy. Afterload, what's it? It's the pressure against which the ventricle eject. The aortic pressure in left ventricle, the pulmonary pressure in right ventricle. I've been saying this since the beginning. So at a constant preload, which means the amount of blood that was coming into the heart, is constant, and with a decrease in afterload, the stroke volume would be increased. But think, the resistance offered by the vessels to the blood which is going in is increased, the stroke volume would be decreased. It's Ohm's law. If the resistance increased, the current can't flow with ease. So when the resistance, which is the afterload, is decreased, the blood can move out with ease, which means the stroke volume is increased. In pressure volume loop, the contraction begins at the same EDV, which means EDV is over here. It's the same, but must reach a higher pressure to open the aortic valve over here. So it has to reach a higher pressure. The AV valve closes at higher ESV. So what? The AV valve will close at higher ESV over here. What happens? So the stroke volume, see, if it increases and if it reaches over here, this is what we're going to get. The curve shifts a bit. So what happens over here? Wait. It's a mess. The contraction begins at the same EDV. So the contraction begins over here, must reach a higher pressure to open the aortic valve. So the pressure over here has to be over here. What does it say then? The aortic valve closes at a higher ESV. It's a curve. It has to close over here. And what happens? It has to follow this line. So why is my iPad acting up? So it has to close over here. It has to close over here because it has to maintain this line. It respect this line. So it will close over here, and what? The relaxation will happen. So what's compromised over here? The stroke volume is decreased over here. So when the afterload or inotropy, let's say the afterload is increased, what happens? The resistance offered by the what, let's say if you're talking about the left side aorta is increased. So what happens? The amount of blood which can be pushed out is decreased. So the stroke volume is decreased. Now, inotropy. What's inotropy? The contractility. So it shifts the ESPBR upwards and towards left. So this would come over here like this. So what happens over here? Contraction begins at the same EDV, it reaches a lower ESV. So it begins over here, it reaches, oh my god, it begins over here, it reaches over here, a lower ESV. Okay, because the volume shifts from A to over here. So what happens? The width of this graph is increased, which means the stroke volume is increased with increase in inotropy. But the other case, when the afterload was increased, afterload, the resistance. When the resistance is increased, what happens? The amount of blood, the stroke volume is decreased. I know this part is a bit too boring, but you have to study to get the marks. In isolated cardiac muscle, positive inotropy increases degree and velocity of shortening. Facts, leave it. Oh, we come to this Frank-Starling law. Cardiac function curve. So this is the cardiac function curve. What's the cardiac function curve? It's the relationship between the right atrial pressure. It is the relationship between the right atrial pressure and the cardiac output. So, right atrial pressure represents the preload. That means the amount of blood that comes to the heart. So, if the right atrial pressure increase, the cardiac output has to increase. Okay, so think. So, this is the right atrial pressure. So, if we follow the line, as we move like this, what? The right atrial pressure is increased. So, it increases slowly. As we move towards the right, the cardiac output is increased as well. Now, mechanism, intrinsic mechanism. So we have the heterometric autoregulation, the Starling law. What does it say? The increasing preload increases the cardiac output, the stroke volume. So increase in cardiac output independent of nervous or hormonal stimulation. It's just based on the length and the stretchability of what? Of the cardiac myocyte. Okay. Limitation. What is the limitation of this mechanism? The curve reaches a plateau at 30 liter per minute. Somewhat over here, it is a plateau. So the pump, it pumps out 2.5 times the venous return as a normal condition. So once it reaches a limit, it goes to a straight line. It doesn't increase the further state. It keeps its saturated point, which was 13 liter per minute. Okay. Then we have the hyper-effective heart, which means the slope has to increase. So this is the hyper-effective heart. So that means the higher cardiac output for the same RAP. Okay, think. When does it happen? When we increase the heart rate, due to sympathetic stimulation, the cardiac output is increased, isn't it? Just think, when does sympathetic stimulation happen? When we are in a situation where we get tensed. So our body has to do a bit more work. So our body demands more blood. So as we said, by different mechanisms, the venous return is increased. So when the venous return is increased, the right atrial pressure, the cardiac output is increased. First thing is increasing the heart rate. Next thing is increasing the inotropy. What happens? Inotropy. At the same right atrial pressure, what happens? The contractility of the heart is increased due to sympathetic stimulation again. So what? It can push out more blood. decreasing in afterload, which means due to the vasodilation and decreasing in arterial blood pressure. Wait, yeah, afterload was what? It was the resistance offered by the vessels to which we are pushing out the blood. So think, when the vasodilation occurs, what? The vessel becomes big, the diameter becomes big. So we have more space for the blood to be pushed into. So what happens? Afterload decreasing, decreasing afterload helps to increase the cardiac output. Hmm? Maximum cardiac output can exceed 30 liters per minute. It can exceed, okay? A fact. So again, what's hypereffective heart? Hypereffective heart means we have a higher cardiac output for the same RAP, right atrial pressure. When do we have it? When we have it when we increase the heart rate, when we increase the inotropy, and when we decrease the afterload. Okay. Now we have the hypereffective, the opposite. It goes down. So what happens at the same constant RAP? The what is compromised? The cardiac output is compromised, so it's decreased. So when does it happen? It happens when we decrease the heart rate, when we decrease the inotropy, and we increase the afterload. So when we have an increased resistance, the amount of blood the heart can push out is decreased. So the maximum cardiac output decreases below 13 liter per minute. What was 13 liter per minute? It was when when our cardiac output reached a plateau. But in case of hypereffective heart, it can cross the plateau. It can go above 30 liter per minute. In a hypereffective heart, when we when we increase the afterload, when we decrease inotropy and preload, heart rate, my bad, we get a decreased cardiac output. When we decrease the heart rate, when we decrease the inotropy, and when we increase afterload. Oof, I'm glitching. So now we have a thing called as cardiac reserve and hypertrophy. What's cardiac reserve? Cardiac reserve is the maximum increase, the percentage of increase in cardiac output above the normal due to increased body needs. So what? When we do some work in which our body needs more blood, the cardiac output is increased. So let's say X was our normal cardiac output, the need to satisfy the basic need of our body, X. But when we do a high endurance work, something like when our body requires more blood, X plus something happens. So that plus the addition of the extra work, the extra cardiac output is the cardiac reserve. So X plus twice the cardiac output is what's the cardiac reserve in X plus 2X? The 2X is the cardiac output, cardiac reserve. So the total cardiac output would be 3X, X plus 2X. And that X was the normal cardiac output, 2X is the cardiac reserve. Normal cardiac output plus the cardiac reserve gives the total cardiac output in case of increased work done. So values. Normal adult has a reserve of 400% from the normal. Well-trained athletes can go up to 600%. These are just facts. 200. Heart failure, nothing is going out. Heart can't push out blood. So it's 0. Cardiac reserve depends on what? Cardiac output was controlled by heart rate and stroke volume. So what affects the cardiac reserve? What's cardiac reserve? It's an increased cardiac output, the increased amount of cardiac output. So heart rate, obviously it affects. How? During maximal exercise, maximum heart rate gives, it's an equation. Heart rate reserve, maximum heart rate reserve is 220 minus the age. So let's say if I'm 10 years old, so what would be my maximum heart rate in case of maximum exercise I do when my body requires the most amount of blood, and I'm 10 years old. So my heart rate could go up to 220 minus 10, which is 210 beats per minute. Okay, that's the heart rate reserve. So 210 is my heart rate reserve. Mm. Minus, I mean 210 minus my normal heart rate. Now for the increased heart rate, the reserve, sorry, the reserve of heart rate, the increased reserve of heart rate goes from 75 to 200. So that's what I said. If I have a reserve, I mean, if I have my maximum heart rate of what? 210, if I subtract 75, I get the heart rate reserve, the difference between the normal and the increased heart rate. Now, stroke volume. What's stroke volume? It was the amount of blood that was pushed out by the ventricle per beat, per each beat. Yeah. Stroke volume increases from 70 to 200 depending upon the maximum exercise we do. Via what? Increasing the end diastolic volume. How? By increasing the preload, the stretch of the cardiac muscle inside the ventricles increase. So what do we get in return? We get an increased contraction. Next thing, decreasing in ESV, the stroke volume, I mean end systolic volume. So what happens? Positive inotropic effect has pushes out more blood from the ventricle. So what? The remaining blood inside the ventricle is reduced, which means there's a decrease in end systolic volume. Am I clear? Then we have cardiac hypertrophy. We'll discuss about it. I don't. Yeah, we have a thing about it. So, what's cardiac hypertrophy? As I said, it's an increase in the number of muscles. Okay, so the thickness. So you have two types. One is eccentric hypertrophy, which means, see, this was my normal heart. This was the volume. So what happens over here in eccentric hypertrophy? The whole ventricle becomes large, so the volume is increased. Okay, so ventricular wall, so the ventricular thickness, the mass is increased just by 50%, a minimum, at least. I mean, not so much, a bit. It's about 50. Hmm? And the ventricular volume is also increased, which increases the end diastolic volume. Uh, Causes. Well, how do we increase uh, the hypertrophy in case of volume overload? It's because of the high preload that comes to the heart. So when we do some exercise or something, our venous return is increased. That means the preload is increased. So what happens? The heart adapts to the increased preload by slowly enlarging, I mean increasing the capacity of what? The ventricle. So in case of endurance exercises of moderate intensity or high intensity, like long distance runners, so in case of marathon runners, their heart would be a bit more bigger than the normal heart due to what? Eccentric hypertrophy, which means their ventricular volume is increased. Now the benefit of eccentric hypertrophy is it enables the heart to pump greater stroke volumes. Because why? Why? Because we have an increased end diastolic volume, isn't it? Next thing, the pressure overload hypertrophy, which means there's an increase in afterload. Now think, over here what happens? Increased ventricular thickness to compensate the increased afterload without increasing in ventricular volume. So the ventricular volume is maintained, but the thickness is increased. Why? When does it happen? It happens due to the exposure of prolonged high afterload. Let's say there's a person with increased hypertension. Could be anything, atherosclerosis, something. So what happens? Slowly, the blood, I mean, the heart buffs up, like gets bigger to push out, to overcome the resistance offered by the vessels, whatever it let it be. So when there's an increased afterload, the heart does more work to like build up muscle to push out the amount of blood. In case of strength training too, okay, because what, in strength training the afterload is increased by different mechanism. I'll tell you later, I mean if it's needed. Benefits. What's the benefit of concentric hypertrophy? So let me tell you, this is the normal heart. If in concentric hypertrophy, this is a normal heart. See, the thickness is increased, but the volume is same. Okay, the benefit, it enables the heart to pump with greater strength. Over there it was the greater what? output, cardiac output, stroke volume. Disadvantage is decreasing in ventricular compliance, means the ventricle can't go a bit more, like stretch a bit more, because there are like a lot of muscle fibers. So when there are like bunch of muscle fibers, it can't stretch, it can't like go easy, it can't like go flaccid, it can like, yeah, it can't accommodate too much blood easily. Performance of isolated cardiac muscle. So think I just took one strand of cardiac muscle. I mean, yeah, a bunch. I isolated. I took it from the heart and I kept it somewhere else. Now, indicators of this is degree and velocity of shortening. So the performance of an isolated cardiac muscle depends. It's indicated by two things: degree and velocity of shortening. So, four factors affect the performance. What? Effect of afterload. So increasing the afterload means increasing the resistance to the flow decreases the degree of shortening and the degree of velocity, decreases the velocity of shortening. So when there's an increased afterload, both the degree and velocity of shortening is decreased. Effect of preload. What? When the preload is increased, the degree of shortening and the velocity of shortening is increased. Why? Frank-Starling law. Yeah. Next, the effect of inotropic state. Positive inotropy means the heart can contract with a greater strength. The degree of contractility is increased. So what happens in positive inotropy? The degree of shortening and the velocity of shortening is increased, because that's why it's called as positive inotropy. Effect of increasing frequency of stimulation. So let's say this is my heart cell and I keep on stimulating it. So what happens? Increasing the frequency of stimulation of the heart increases its force, means it increases the inotropy to reach a plateau. So there is there's an increase like this until it reaches a plateau. This is a plateau. This phenomena is called as staircase phenomena, because every time you stimulate, there's an increase in the force, but at a point it reaches a plateau because we can't do more work. It gets exhausted. So this is called as staircase phenomena or else Sharpe phenomena. What does it say? Increasing in frequency later on increases the force until it reaches a plateau. Why does it reach a plateau? It's because why do we have a phenomena so called staircase phenomena? It's because every time we stimulate the muscle, more and more calcium is allowed to enter inside the cell. So at a point, the calcium gets saturated inside the cell, isn't it? Because there are like limited amount of muscle fibers. So once it reaches a saturated point, that's when we get the plateau. Until the plateau, calcium entry is directly proportional to the force of contraction. But once it reaches the plateau, no matter how much amount of calcium goes in, it can't contract with an increased force. So that's staircase phenomenon. Then we have the length tension relationship. Summary. So what does it say? Passive length tension means passive tension increases during the stretch of cardiac muscles. That means when in case of the ventricle relaxation, the blood goes in. No work is done. It just receives the blood. So what happens? That's passive. So there is an increase in tension during the stretch of cardiac muscles. The more blood that comes into the ventricle stretches. So the tension is developed inside the ventricle, but that's passive. It's not doing any work. It's just holding the blood. Then there's an active length tension relationship. What does it say? Frank-Starling law. What's that? Within limits, active tension is directly proportional to the preload. That means more preload we give, the heart can contract with the more force. The contractility is increased. So that's active tension. So the heart is doing the work, it's contracting. So it's active process, isn't it? So the length tension relationship gives passive length tension is during the stretching of cardiac muscle during whatever it is, the ventricular relaxation. Active tension means active tension is directly proportional to the preload. So more preload, more active tension, means the heart can contract with a greater force. So that's pretty much it. I guess I have covered every important topic for this module. Yeah, I did. So just go through this. You can look through this live again and again until it's clear. If you have any doubts, you can text us on our Insta page, Instagram, Osium, osium.med. So you can contact us through that if you have any doubt. So yeah, that's it. I hope everyone does a great job for his exam on his exam paper. So relax. There's nothing to worry. No matter, it's just another day. So sleep well, eat well, do your best, leave the rest. That's pretty much it. Don't worry, everything's gonna be fine. So I'm gonna end this live session over here. We'll catch up again with another module